Hello class, here in lesson number 8 we have factoring higher degree polynomials, and what they're just going to go over here is simply that we're dealing with integers. If you read these first couple of paragraphs, it's talking about you can factor beyond integers, and in that case you actually have an unlimited number of factoring opportunities, but we have limited ourselves to using simply integers, whole numbers, and at the end we read here at the bottom of page 47 that that although this sort of factoring is sometimes useful, we will assume that when we speak of factoring polynomials, that we're referring to finding factors that are either integers greater than 1 or polynomials having coefficients and constant terms that are integers. Okay, so if we look over on page 488, we have various examples of what we've learned on how to factor, and if you just look at these 5 examples, you'll be able to see that we can factor out the greatest common factor. So in this case we simply factored out 5x. On the second one we can factor a polynomial in the of the form x squared plus bx plus c by factoring out or factoring c into two numbers, and we ended up in this case with this example of x plus 3 and x plus 5. We also factor the difference of two squares. We recognize that we have two squares, two perfect squares that are being subtracted. So we can then write them in the form of the, if I were to go as far as to say the square root of each of these terms, right? But we wrote them as a squared and b squared, so we're looking for the a and the b, and the a and the b are basically the square roots of a squared and b squared. So if we're looking at 4x squared, we would have factored that into 2x, and then negative 3, we would have had a plus and a minus 3, and that would have given us the answer there. Then we have factoring the trinomial square as the square of a binomial. We recognize that we can have an opportunity where we have a trinomial that's basically the square of a binomial. In this case, we see 2x minus 3 being squared. And lastly, we did that more complex where we have an ax squared plus bx plus c polynomial, and we have to look at all the different factors of a and c, and they have to add up to b. So now we're going to have to take just a look at some of these examples. We've applied these methods primarily to factoring second-degree polynomials. There are other methods studied in advanced algebra for discovering factors of polynomials having higher degree. In this lesson, we will factor some higher degree polynomials by the methods we already know. So this is kind of a review, okay? And we have the basic procedure is to begin by factoring out the greatest common factor of the terms of the polynomial, then look at the remaining factor to see if it is either a trinomial square or the difference of two squares. Okay, so if it is, then we factor it out. If not, then we look for other combinations. So we try to find first the difference of two squares. Obviously, if we look at example number 3, we have two squares that are being subtracted, or it could be the polynomial or the trinomial square is this as the square of a binomial. So we have number. So we're looking for 3 or 4, and if it's not either of those, then maybe it's 5. Okay, where we have a little more work to do, or it could really even be 2. So we want to take a look at the first example. We have x cubed plus 4x squared plus 4x, and again we find the greatest common factor is x, and it gets factored out. I'm not going to do these on the board, they've already done them well here, and so we end up with x times this polynomial x squared plus 4x plus 4, and we would determine based on our knowledge and doing a little bit of work there that this is a trinomial square, and so we could factor it. And how do we know it's a trinomial square? Well, just take a look at the factor of 4 and say we know 4 could be 2 times 2, right? because that's a square. That's a perfect square. And what happens when we have 2 times 2? Well, in our binomial scenario, we would end up multiplying those 2's times x's, and we would end up with 4x, right? 2x plus 2x. So that's really the hint. First off, that we have our first and our third term are going to be squares. They're perfect squares. And then we have to determine whether or not the addition of those x terms that we're going to create, and again, if it's 2 times 2, then there would be a 2x and a 2x, because again, we're just dealing with x squared, then that would work because it would add up to 4x. So that is example 1. Example 2, we have 3x cubed minus 27x. Okay, now again, we're looking to factor out the greatest common factor. That's the first thing. We have some complexity here that doesn't look like the ones that we were doing previously because they've added some terms, and you have to undistribute. And again, I said that that's not a word, but you're doing the reverse of distributing. You're pulling something out, and our greatest common factor here would be 3x, right? So we'd end up with 3x times this binomial x squared minus 9. Now, I look at x squared minus 9, and I already recognize that opportunity here of the difference of 2 squares, because I have x squared, I have 9. Those are 2 perfect squares, and they're being subtracted, okay? And we would then end up with the answer of 3x times these 2 binomials, x plus 3 and x minus 3. So let's move to example number 3. We have x to the 4th power plus 2x cubed minus 15x squared. Now the greatest common factor here is x squared, only x squared, because the coefficients do not have any common factors other than 1. So we factor that out, and we end up with this x squared times the trinomial of x squared plus 2x minus 15. Now the question is there an opportunity here? Now, we know that they're not squares. 15 is not a perfect square, so we know we're going to end up dealing with several factors here. And right off the top of my head, if I start thinking of the factors of 15, I think of 5 and 3, right? Now, being that I'm dealing with the 2x over here, now I have to think, well, if I can get this to sort of match up to 2x, positive 2x, and I have a negative 15. So in my mind, I'm thinking, well, if I had a positive 5 and a negative 3, right, that would work, because that would be a positive 5x and a negative 3x, and when I combine them, that would be a positive 2x. So we would be able to factor them, as you can see. And again, I'm just doing this in my mind. I'm recognizing the opportunity. You would eventually have to write these things out, as we see here, and we would end up with the answer of x squared times 2 binomials, x minus 3 and x plus 5. And then lastly, we have 2x to the 5th power plus 2x to the 3rd power. Now, we would just factor out our greatest common factor, and we know that that would be, there's 2 in both of these, so the 2 would be part of it, and the x cubed is the variable to the lowest degree, which I know I can factor out of everything here, so that would be 2x cubed, which is exactly the second term, right? So factoring it out gives us 2x cubed times this binomial x squared plus 1. Now, x squared plus 1, hey, if that would have been an x squared minus 1, I would have recognized the difference of 2 squares, right? Because 1 squared is 1. I would have been able to do it, but because they're being added, we cannot do this. When they're added, we would actually end up with that 3rd term in the middle, and we know that that doesn't work, so this cannot be factored any further, and we would have had 2x cubed times this binomial x squared plus 1. Okay, so really we're just making it a little bit more complex, adding a little more within this whole scenario of factoring. You factor out maybe a term, or a factor, a particular a monomial, let's say, and you factor that out, then you're looking to see, is there more opportunity? And you're always doing that in math. You're always looking for opportunities to factor, because we're just looking at these isolated. When they become part of larger bigger, much more complex problems, you will find that by being able to factor, you're going to be able to derive your answer a lot easier, okay? Because you're breaking down the complexity of the degrees, and if you're able to get to something as simple as we have here, let's say let's example number 2, we have 3x, and we have x plus 3 and x minus 3. And if this were to somehow equal 0, it would be very easy, because we know that if any one of those three terms is equal to 0, then those would be our answers, right? So, but you'll be challenged more, much further, and well, that's the end of this particular chapter.